Welcome to our practical guide on handling heteroscedasticity using weighted least squares, or WLS, regression in Stata. This presentation is designed for students and researchers looking to improve their regression models. We will explore why and when to use WLS and provide a step-by-step guide to its implementation in Stata. Imagine you're studying the relationship between income and savings. You might find that the variation in savings is much larger for high-income individuals than for low-income ones. WLS helps us account for this changing variance. First, let's understand the core problem that WLS is designed to solve: the difference between an ideal statistical world and the messy reality of real-world data. In an ideal statistical world, our data would exhibit homoscedasticity. This means the variance of the error term remains constant across all levels of our independent variables. Under these perfect conditions, the ordinary least squares, or OLS, estimator is the best linear unbiased estimator, or BLUE, providing us with efficient and reliable results. However, real-world data rarely conforms to this ideal. We frequently encounter heteroscedasticity, where the variance of the error term changes depending on the level of the independent variable. For instance, consider the relationship between income and savings. The variability in savings often increases significantly as income rises. This violates a fundamental assumption of OLS. When heteroscedasticity is present, OLS becomes inefficient, meaning its estimates are not as precise as they could be. More critically, the standard errors produced by OLS become biased. This bias directly impacts our hypothesis tests, such as t-statistics and p-values, making them unreliable and potentially leading us to draw false conclusions from our research. For example, OLS would treat the savings data of a billionaire with the same statistical certainty as that of a student, which is clearly inappropriate given the vastly different scales of their financial variance. So, how do we navigate this issue of variance in our models? This decision framework provides a clear roadmap. We always begin by running a standard ordinary least squares, or OLS, regression. Following this, the crucial next step is to perform diagnostic tests to check for heteroscedasticity. This involves visual inspection using tools like the RVF plot and formal tests such as the Bruch-Pagan test. If these diagnostics indicate no heteroscedasticity, then your OLS results are valid, and you can stop there. However, if heteroscedasticity is indeed present, we then ask a second critical question: is the underlying structure of the variance known, or can it be modeled? If the variance structure is known, or can be successfully modeled, then approaches like weighted least squares, including feasible WLS, or the specialized VWLS command for grouped data, are the most efficient solutions. If, on the other hand, the variance structure is unknown or appears random, the best practice is to continue using OLS, but to correct your standard errors by employing the VCE robust option. Stata offers several commands tailored to different assumptions about variance. The standard regress command assumes homoscedasticity and is best for clean, well-behaved data. If you have unknown heteroscedasticity, regress with the VCE robust option is a great choice. It corrects the standard errors, making your inference valid, but it does not improve the efficiency of the coefficient estimates themselves. The focus of our talk, weighted least squares, is implemented using regress with analytic weights, WLS. This method increases efficiency by producing smaller standard errors, but it requires you to correctly estimate the weights. Finally, the VWLS command is a specialized tool used when you have known variance, such as in grouped data or data from physics experiments. It's less common in general social science research. The core principle behind weighted least squares is quite intuitive. We place more trust in data points that are more precise. Our objective is to minimize the weighted sum of squared residuals, as expressed in the formula you see on screen. Min sum Wi times yi minus y hat I squared. The crucial element here is the weight, denoted as Wi. Observations characterized by low variance are inherently more reliable. These data points are assigned a high weight, acting like a strong anchor that draws the regression line closer to them. In contrast, observations with high variance are less reliable. They receive a low weight, exerting minimal influence on the regression line, much like a light feather. This means WLS effectively prioritizes the more dependable information in our dataset, leading to more efficient coefficient estimates. For instance, in a study of company profits, a large, stable utility company with predictable earnings would receive a high weight, while a volatile tech startup with unpredictable earnings would be given a low weight. This powerful weighting mechanism, however, relies on some important assumptions, which we'll review next. For weighted least squares to be effective, 3 key conditions must be met. First, the model must be linear in parameters, just like in OLS. Second, the errors must be independent or uncorrelated. The most crucial assumption is that the weights are correctly specified. Ideally, the weight Wi should be the inverse of the error variance, 1 over sigma I squared. This leads to a critical trade-off. If your weights are correct, WLS is more efficient than OLS, leading to smaller standard errors. But if your weights are wrong, WLS can be less efficient than OLS. Since we rarely know the true variance sigma I squared, we use feasible WLS, or FWLS. This involves estimating the variance from the residuals of an initial OLS regression. Be aware, however, that misspecifying these weights can make your FWLS estimates worse than standard OLS with robust errors. A common question with weighted least squares is how to interpret its coefficients. The good news is that the economic meaning of a WLS coefficient, represented by beta, is exactly the same as an ordinary least squares. It signifies the change in the dependent variable for a 1-unit increase in the independent variable, holding all other factors constant. The fundamental difference between WLS and OLS isn't in what the coefficient means, but in how it's estimated. WLS allows the regression algorithm to prioritize more reliable data points, those with lower variance, over noisier ones that exhibit higher variance. As you can see in the visual, the WLS line is pulled more strongly towards the dense clusters of data, which represent these more precise observations. For instance, in a regression of wages on education, a WLS coefficient of 0.8 on education means that, on average, 1 additional year of education is associated with an 80-cent increase in hourly wage. This interpretation is identical to OLS, but the 0.8 value was estimated by giving more weight to individuals whose wages are more predictably related to their education. We're now looking at the specific Stata syntax to implement weighted least squares using analytic weights. The primary command is regress, followed by your dependent and independent variables. The crucial part is adding the A-weight equals invar option. It's vital to understand what invar represents. Stata's A-weight option assumes that the variance of the error term is inversely proportional to the weight you provide. Specifically, var of E equals sigma squared divided by the weight. Therefore, the variable you input for A-weight must be the inverse of your estimated variance for each observation. For example, if you've estimated the variance and stored it in a variable called var hat, your weight variable would be 1 over var hat. As a best practice, and to provide a safeguard, we strongly recommend including the VCE robust option alongside A-weight. This ensures that even if your weight function is slightly misspecified, your standard errors will still be robust and your inference valid. This slide introduces Stata's specialized VWLS command, which stands for Variance-Weighted Least Squares. You should use this command only when you have truly known standard deviations or are working with group data where the variance structure is explicitly given, rather than estimated. The syntax is straightforward. VWLS depvar indepvars SD SDvar, where SDvar is the variable containing the known standard deviations. This contrasts significantly with the regress command using analytic weights, AW, which is for feasible WLS when variance is unknown. A key difference lies in scale estimation. VWLS assumes the error variance, sigma squared, is fixed at 1, while regress AW estimates it from residuals. Furthermore, VWLS takes the standard deviation as input, whereas analytic weights for regress require the inverse variance. Therefore, VWLS is best suited for scenarios like group data or specific applications in physics where variance is precisely known, making it less common in general social science research compared to feasible WLS. We begin our feasible WLS workflow with the crucial first step, diagnosis and establishing an OLS baseline. First, we run a standard ordinary least squares regression, using wage as our dependent variable and EGIC and EXPER as predictors. Immediately following this, we perform diagnostics to check for heteroscedasticity. The residual versus fitted values plot, generated by RVF plot, clearly displays a distinct funnel shape. This widening spread of residuals as fitted values increase is a classic visual indicator of non-constant variance. To formally confirm this, we use the Bruch-Pagan test via a stat-het test. The test yields a p-value, prob greater than chi-square, of 0.0000. This extremely low p-value leads us to strongly reject the null hypothesis of homoscedasticity. Our data unequivocally shows the presence of heteroscedasticity, signaling that our standard OLS estimates are inefficient and their standard errors are biased. This clear evidence sets the stage for our next steps in modeling the variance itself. Moving on to step 2 of our feasible WLS workflow, modeling the variance function. The core idea here is to estimate the unknown variance by regressing the squared residuals on our original predictors. We begin by extracting the residuals from our initial OLS regression using the predict-residuals command. Since variance must inherently be a positive value, we log linearize these squared residuals. This involves generating a new variable, ln_squared resid, by taking the natural logarithm of the squared residuals, which guarantees that our variance predictions will always be positive. Next, we model this transformed variance by running a new regression. Here, we regress ln_squared resid on our predictors, such as educate and expert. This regression helps us understand how the variance changes across different values of our independent variables. Finally, we use this model to predict the fitted values, ln_var hat, which represents the predicted log of the variance. This predicted log variance is a crucial intermediate step. In the next stage, we will exponentiate it to get the actual predicted variance and then invert it to construct our WLS weights. In this crucial step, we transform our predicted variance into the actual weights for our weighted least squares regression. First, recall that in the previous step, we modeled the logarithm of the squared residuals, so we need to back-transform this prediction to get the estimated variance. We do this using the gen_var_hat equals exp of ln_var_hat command, which applies the exponential function. Once we have the estimated variance, var_hat, we can calculate the WLS weights. As discussed, WLS requires the inverse of the variance, so we generate our WLS weight variable using the command gen_WLS_weight equals 1 over var_hat. The table on the right from the Stata data editor shows how these variables come together. You can see the original residuals, the log of the squared residuals, the estimated variance, and finally, the calculated WLS weight for each observation. It's always a good practice to verify your newly created weights with a summarized WLS weight command to ensure they are within an expected range and don't contain any missing values or extreme outliers. With our weights now calculated and verified, we have completed step 3 of the feasible WLS workflow. We've reached step 4, where we execute the weighted least squares regression using the A-weight option with the WLS weight variable we meticulously calculated. The command regress wage ed exper A-weight equals WLS weight instructs Stata to assign greater importance to observations with higher values in our WLS weight variable, effectively trusting the more precise data points more. A crucial technical detail here is that Stata automatically rescales these weights so their sum equals the total number of observations, n. This normalization, which you can see noted in the output as sum of weight is 2.3230e plus 0.1, is essential for preserving the correct magnitude of our standard errors. It ensures that our WLS standard errors are directly comparable to those from an OLS regression. Having successfully run our weighted regression, the next and final step is to compare these WLS results side by side with our initial OLS findings to clearly see the impact and improvements. Here we compare the results from our initial ordinary least squares, or OLS, model in column 1, with our final weighted least squares, or WLS, model in column 2. Notice that the coefficients for ED and X are very similar between the two models. This is a common outcome, as WLS primarily aims to correct inference and improve precision, not drastically alter the point estimates themselves. The most important comparison lies in the standard errors, which are shown in parentheses. For the ED variable, the standard error decreased significantly from 0.058 in the OLS model to 0.042 in the WLS model. This reduction in the standard error is a direct demonstration of the improved efficiency gained by using WLS, meaning our estimates of the coefficients are now more precise. This enhanced precision allows for more reliable hypothesis testing and stronger conclusions from our analysis. To summarize, our first best practice is always to diagnose before you treat. It's crucial to confirm heteroscedasticity is present using graphical tools like RV-plot and formal tests such as a stat head test. Never apply weights without clear evidence that they are needed. Second, feasible weighted least squares is the most efficient method when you can clearly model the variance structure. This involves running an initial OLS, modeling the log of squared residuals, predicting the variance, inverting these predictions for your weights, and then executing the final weighted regression. However, if modeling the variance function feels too complex or you're uncertain about its true form, the robust alternative, using OLS with VCE robust standard errors, is an excellent and safe choice. This approach correctly adjusts your standard errors for valid inference without requiring you to specify a complex variance model, ensuring your hypothesis tests are reliable, even if it doesn't improve coefficient efficiency.